The Week in the Life sessions follow Daniel, a typical corporate developer, through a week of writing code and improving existing solutions. As a corporate developer, Daniel has recently been assigned to a development team for the BizLogic Corporation. The development team that Daniel has been assigned to is responsible for the maintenance of an in-house CRM application. The CRM application supports users in the local network, as well as remote users outside of the firewall. Because Daniel has excellent exposure to new technologies and their benefits, he was added to the team to improve application performance, stability, and availability for BizLogic CRM. Day 1 focused on back-end solutions, including how to best take advantage of existing hardware resources to increase agility and decrease costs while continuing to ensure reliability and performance. Day 2, this presentation covers best practice enhancements for the middleware tier. This will include objective performance measurement using vTune, using the Intel C++ compiler, adding threading with OpenMP, and measuring threading performance using Intel threading tools. The third day will focus on client-side optimizations. At this phase of implementation, Daniel will need to create a performant client application to maximize user interface responsiveness and minimize any perceived sluggishness. Subsequent days will focus on the need for mobile client applications as well as implementation details. The main focus of these days of development will be on recognizing the need for mobility, ensuring that Daniel's application provides mobile functionality, and ensuring that everything remains performant. Daniel's company, BizLogic, is running a proprietary middle-tier server written in C++. The server is designed to handle multiple simultaneous client connections, connecting to the database server to service requests. Daniel is asked to take steps to optimize this server for optimal performance. Performance tuning requires a multifaceted approach, which can include tuning the operating system and adjusting memory and disk allocation for an application server. This presentation will focus on Intel tools and technologies used to achieve this goal. You will see how Daniel can use these tools and techniques in the accompanying hands-on lab and demonstrations. We'll begin this presentation by discussing the compiler issues. Daniel is wondering if the code is really being optimized enough by the compiler. See how the choice of compiler can make an enormous difference in application performance without necessarily even making any changes to code. As a Visual Studio developer, Daniel is currently using the default Microsoft C++ compiler. He has read about the Intel C++ compiler and is interested in seeing how it can improve his compiled code. He discovers that the Intel C++ compiler plugs into the Microsoft Visual Studio environment, providing all of the benefits without learning a new environment. You will have full source and object compatibility with Microsoft Visual C++ 6.0, and substantial source and object native code compatibility with Microsoft Visual C++.NET. By simply recompiling his code, he gets improved application performance. He also has the option of simply compiling specific application modules with the Intel C++ compiler, then linking them with modules already compiled with Microsoft Visual C++. 32-bit processors benefit from a number of optimizations which require little to no effort to take advantage of. The automatic vectorizer will parallelize his code by such techniques as loop peeling to generate aligned loads and loop unrolling to match the prefetch of a full cache line. Runtime processor dispatch can optionally allow him to build multiple specific targets in order to take advantage of the latest processors while maintaining full compatibility with previous IA32 processors. 64-bit Itanium 2 processors benefit from features such as predication, improved branch prediction, and software pipelining. BizLogic can maximize application performance with advanced optimization features available simply by recompiling source. Predication refers to removing branches from program sequences in favor of predicated instructions which offer inherent conditional execution. Dynamic instruction fetching is more efficient with fewer possibilities for changes of control flow. Speculation performs certain operations out of sequence before they are needed by executing recovery code when needed. This ensures that all instructions are executed properly if the original conjecture was incorrect. The Intel C++ compiler fully exploits the latest multi-core processors while continuing world-class performance on existing processors and architectures. BizLogic runs a variety of different hardware platforms throughout the company. This is no problem for the Intel C++ compiler, since applications running on both 32-bit and 64-bit processors benefit from optimized floating-point instruction throughput. For the IA32 architecture, floating-point instructions are executed efficiently using the stack. Overlapping instructions can put their calculation results in any stack register for improved application performance. Itanium 2 processors can pipeline floating-point loops using directly addressable floating-point registers. Data prefetching consists of specific instructions to move reference data items as close to the processor as possible using cache memory before they are actually required. This effectively hides memory access latency and significantly improves performance in many compute-intensive applications. This process occurs automatically and occurs completely within the compiler, therefore allowing the source code to remain portable. Auto-parallelization improves performance on multi-core, multiprocessor, and hyperthreading-enabled systems by automatically threading loops. This generates the multi-threaded code when it detects parallel loops that can be executed safely in parallel and eliminates the need for you to understand iteration partitioning, data sharing, thread scheduling, and synchronizations. This can help BizLogic applications to fully exploit the fully available processing power of the system. The Intel C++ compiler also fully supports the OpenMP standard for portable multi-threaded application development for both fine-grained and large-grain threading. These directives are an easy way to increase performance through the conversion of sequential code to parallel code with minimal impact to existing code. Like most developers, Daniel considers the debugger to be an integral part during the development process. The Intel debugger is a component of the Intel compilers that helps programmers locate runtime programming errors in their code using either a command line or GUI-based environment. The Intel debugger can be used with a variety of compilers, including the Intel C++ and Fortran compilers, GCC and G++ compilers, and Microsoft compilers. Both Linux and Windows systems are supported. The debugger fully supports debugging code that has been optimized for specific hardware architectures. This is significant, considering the amount of reordering that occurs with optimized code. Most debuggers disallow this due to the effort of synchronizing source code with the compiled code. Unfortunately, the very process of optimization can sometimes cause bugs. Being able to debug fully optimized code allows the most accurate analysis of code in order to track down subtle errors. The Intel debugger enables debugging of multi-threaded applications on multi-core architectures with the ability to switch focus between threads, list all threads, start and stop threads in a unified fashion, set breakpoints, and more. A GUI-based thread panel allows Daniel to view all thread details when a thread is created. Daniel knows that the hardware landscape changes too often to be locked into any technology. The Intel C++ compiler functions across a wide range of existing and cutting-edge Intel processors on both Windows and Linux systems. This makes it easy to stay at the forefront of processor technology by using tools straight from the source. Daniel can take advantage of higher levels of performance and features for servers and workstations with 64-bit technology, retaining full compatibility with existing 32-bit IA32 processors. The Intel C++ compiler provides support for generating both 32-bit and 64-bit executables. You can develop 32-bit applications targeting processors such as the Intel Pentium or AMD Athlon. You can also develop applications for both Intel Extended Memory 64 processors, also known as EM64T, or the AMD Opteron. Not every organization within BizLogic is completely standardized on the same development platform. Fortunately, the Intel C++ compiler enjoys substantial compatibility with the Linux GNU C++ compiler, supporting the C++ application binary interface, and using the GNU C++ runtime library enabling binary compatibility with C++ object files. It also plugs into the Visual Studio environment as an optional compiler and can take advantage of switches, makefiles, and library and DLL formats. It's easy to control the build process by mixing the native Visual Studio compiler with the Intel compiler as necessary, or to improve performance throughout by switching completely. The Intel C++ compiler is also fully compliant with all relevant ISO and ANSI standards. Optimizing is more than an on-off switch. The Intel C++ compiler can use Profile Guided Optimization, or PGO, to help Daniel take better advantage of the processor architecture. Instruction paging, cache memory, and better branch predictions leads to better performance by reducing instruction cache thrashing, reorganizing code layout, shrinking code size, and reducing branch mispredictions. PGO works in 3 steps. The application is built with instrumentation to measure real workloads from runtime. As the application runs, it performs actual operations, all the while storing information regarding its performance. This stored information, along with information derived through static analysis, is then fed to the compiler, which is able to optimize the code in a highly specific fashion. With actual runtime behavior capture, the optimizer can generate better code. This allows Daniel to create tightly optimized executables based on their exact usage within the company. Interprocedural optimization, or IPO, is another optimization that can significantly improve performance of applications containing many small or medium-sized functions. Its effects are most pronounced when such functions are called within loops. IPO works by decreasing the number of branches, jumps, and calls within code. Wherever possible, code is inline for further reduced overhead. Cache usage can also be improved by certain data layout optimizations. IPO is a simple process. Source code files are first compiled with IPO enabled in order to generate intermediate views of the source code containing summary information to be subsequently used for optimization. This information is then used across all modules in order to create a holistic plan to perform function inlining and other related optimizations in the second compilation step. Frequently executed functions are inlined by copying the actual function body to the calling location. This removes the need to prepare parameters and the actual function call branch. The final linked application is more efficient with improved performance. Daniel knows that creating great software encompasses a number of best practices. Writing solid code is the most important factor, however, can seldom be achieved in one attempt. Testing becomes critical to produce the best product possible. That said, testing takes time. It is important to test all code thoroughly. Seldom used code paths may not be tested as well as other code. The code coverage tool ensures that all code is tested sufficiently. A visual presentation of code coverage makes it clear what sections are being tested. It also shows the difference in test coverage between different runs. This can be useful for better determining the path that the code takes. As code is modified and retested, the compiler test prioritization tool saves significant time by suggesting tests based on specific changes. Advanced dependency checking can analyze profile data from previous runs, along with changes to components in order to guide the testing process. This reduces the number of tests to perform, thus saving time, especially in large-scale applications where testing may be a major bottleneck. Some common programming errors can be caught at runtime for Visual C++.NET applications. Perform stack frame runtime error checking, including initializing local variables to non-zero values, detection of overruns and underruns of local variables, and verification of stack pointer corruption. Daniel knows his trade inside and out, but tools like these allow him to focus his time and efforts where they are needed most. Intel offers a variety of performance analysis tools to assist in determining how to achieve the best results from your application. Using additional plugins, such as the Intel threading tools, can allow developers to further dig into the operation of their code to find exactly where to tune it. Daniel is accustomed to big iron running in the server room. With threaded, dual and multi-core processors becoming available for the desktop, high-end computing power is no longer relegated to the server room. Today's cutting-edge multi-core processors will be tomorrow's commonplace. The processor race is shifting as raw processing power is no longer the only deciding factor for performance. While single processor performance is reaching its limit, The benefits of multiple processors and multi-core are quickly ceasing to be an option. Taking full advantage of multiple concurrent threads across laptops, desktops, and servers requires a change in coding strategy. Applications need to be threaded to realize the potential performance that these new architectures can provide. Daniel knows that threading your applications correctly can be time-consuming. Even done properly, it increases the complexity of the code, thereby making it more susceptible to bugs that are hard to catch using traditional troubleshooting techniques. Unfortunately, introducing and encountering such bugs is often easier than reproducing and isolating them. In addition to common coding problems, developers will need to be aware of a different class of errors entirely. Situations such as deadlocks and race conditions are only present when multiple threads are in use. Such errors sometimes occur in single-threaded application development when calling out to multi-threaded components. But debugging your own applications introduces a new level of complexity. If added improperly, multiple threads can do more harm than good to an application. Each thread must be tracked by the processor for scheduling and execution. The more threads, the more context switches to run those threads. Multi-core and hyper-threaded processors can schedule more than one thread at a time, but single-core processors must switch for every active thread. Making efficient use of available resources can mean the difference between high and low performance. The traditional single-threaded application has a strong advantage to the developer in terms of predictability. Because concurrency does not exist, no locking mechanism is ever needed, and data integrity is virtually guaranteed. Following the flow of the application is easy and consistent. Even with multiple threads, a single-threaded processor can only execute operations from one thread at a time, regardless of how many have been created. Rapid switching creates the illusion of concurrency, but at a fundamental level, the execution of instructions is still fairly deterministic. When threads can truly be executed in parallel, it becomes difficult, if even possible, to predict execution order. The actual execution order of instructions can be influenced by other operations in the same application or other applications across the operating system. This can introduce errors never foreseen. Properly locking data is crucial in order to preserve integrity. Though the benefits are enormous, threading may bring errors to light that only manifest themselves sporadically and may be hard to reproduce. The same code that works fine in a single-threaded environment may well fail with multiple threads. A lack of locking can quickly lead to memory corruption, while the improper use of locking, especially based on the level of granularity, can cause race conditions that bring an application to a halt. Proper threading can bring application performance to new levels, but without the right tools, it may be an uphill challenge to get it to that point. Daniel has some cause for concern regarding code complexity, but fortunately tools come to the rescue again. Intel threading tools can actually help to locate some threading errors before they even occur due to its in-depth awareness of threaded program behavior. They can identify shared and private variable conflicts, locating exactly where in a program an error is likely to occur. The tools can show workload imbalances and maximize performance by maximizing time spent in parallel regions. He can view the critical path of his application to see how threads can be used more efficiently. Armed with that information, he can create the most optimized version of his code. One-click diagnostic help can make it easy to correct issues and take the most advantage of threading capabilities. The Intel Thread Checker can identify 5 levels of threading issues, including information, warning, and error, to allow him to focus on the most important issues. Using the Intel threading tools is easy. The user interface is powerful and intuitive, allowing Daniel to see errors and drill down to the function, line, and variable level. He can see call stack information in order to fully understand the error. He can also arrange issues visually, with full ability to group, arrange, and sort the data based on priorities at each stage of development. He can create threaded applications that are efficient and reliable, discovering potential errors that may not have been discovered until too late. They make it easy to find opportunities to optimize code to create the most optimal flow, gaining an in-depth understanding of the path of the application from one thread to another. They will speed the development process by finding potential and actual errors through a combination of static analysis and runtime checking. Static analysis can find errors before ever executing code, while the advanced runtime checking can catch deadlocks, data races, and more as they occur. All of this allows the developer to concentrate more on the user interface and business logic, confident that parallel code will bring about the intended benefits. The Intel Thread Checker is a plugin that works in the Intel vTune Performance Analyzer to analyze, debug, and verify threaded applications. The Intel Thread Checker makes it easy to locate hard-to-catch multi-threaded errors such as deadlocks, data races, and thread stalls. The Intel Thread Profiler presents multiple views of performance data to discover performance bottlenecks. View runtime statistics broken down by threads or regions within the code. Determine how to maximize the performance of a threaded application by assuring that threads are loaded evenly. This allows a developer to compare various synchronization strategies or algorithms to determine the best choice. Identify performance issues such as synchronization delays, stalled threads, and excessive blocking time by understanding the threading patterns in code by visualizing thread hierarchies and their interactions. BizLogic is a diverse company in many ways, and the server room is no exception. Intel threading tools help them to gain value in both single and multi-core processors. They can discover where data synchronization may be insufficient or incorrect, and how to best leverage parallel processing power. As with many companies, BizLogic runs the best platform for each function. The same tools run in both Windows and Linux environments. They can analyze applications with native Windows or POSIX threading, or applications built with OpenMP directives. Developers like Daniel can use this to determine threading correctness and find performance bottlenecks. Full 64-bit support with Intel Extended Memory 64 technology ensure that both high-end and low-end environments can achieve high performance, even in such scenarios as 32-bit applications running on 64-bit processors. If you're familiar with using the Intel vTune Performance Analyzer tool, you'll be right at home using the Intel Thread Checker and the Intel Thread Profiler tools. Creating a Thread Checker project is the same as creating any other Intel vTune project. Click New Project, and under Category we now have two different options for Analyzer projects and Threading projects. Threading projects gives us a Thread Profiler and a Thread Checker wizard, which both give immediate help on the side. As with other vTune wizards, we'll start by selecting an application. The Thread Checker wizard will update the diagnostics while the activity is running. We don't need to wait until the end. And we'll immediately run this activity as soon as we're done with the wizard. So the application is now starting up within the Thread Checker tool, and the Thread Checker real-time status window will actually show diagnostics as they're ready, even though the application isn't completely finished coming up yet. If we click the flag button, it will update the interface window, and we can already see an event that it's discovered. The application is now finally available. Another diagnostic is ready. We can show that, again in real time. And we'll finish the application. In the output window, you can see that it's done loading the data. You can load the remaining entries. Close the output window for more screen space. And these are all of the issues that the Thread Checker found with the code. You can see that they're categorized by severity: unclassified, remark, information, caution, warning, error. You can set filters, and that will hide certain events on here. The diagnostics provide a lot of information by showing the module where the error occurred, and also providing information such as the line number, the function, and the variable, and then an explanation of the error itself. If you're new to the tool, you can right-click on columns and get help on the column itself. And this provides great information to help you understand about the information that you're seeing. Or if a specific description doesn't give you enough information, there's online help available for that as well. We can view more information by double-clicking an entry. And it brings us to the source view, where we can see both the first access and the second access. And this refers to the two threads that are causing an issue. And you can see where each of them are in the code. The Stack Traces tab shows us the call stack of both of the threads. It gives us an incredible amount of information about the application, how it's running in terms of threading performance. There's great help available through the online help file, through tooltips, quick links using the column help and the diagnostic help commands. It really allows you to perform great runtime analysis of your code with objective tools so that you can locate hard-to-find threading errors. This will let your application perform at its best with as few errors as possible. Powerful multi-threaded applications can require work to prevent errors from creeping in. Using the OpenMP standard, code can be parallelized with significantly less effort in coding and testing. In response to the many challenges facing programmers regarding multiple processors and platforms, the OpenMP Architecture Review Board was formed in 1997 by a number of high-profile companies such as Sun, IBM, SGI, HP Compaq, and Intel. Their work resulted in the creation of the OpenMP API to support multi-platform shared memory parallel programming in C, C++, and Fortran on all platform architectures including Unix and Windows. It is a portable, scalable model, providing a simple and flexible interface for creating parallel applications on both desktops and supercomputers alike. OpenMP allows you to add parallel features to your applications at two levels. Pragmas are compiler directives embedded in the code and provide specialized instructions to the compiler. OpenMP pragmas specify how to assign work to one or more threads. OpenMP allows you to specify code to run in parallel in addition to visibility and synchronization management. OpenMP features can also be added using specific API functions. Daniel doesn't want to learn threading at a low level. He understands the concepts, he knows where to apply them, but he is also aware of the potential pitfalls. Pragmas make it easy to test the effect of threading without wholesale code re-architecting. By utilizing pragmas, actual logic code remains largely untouched. When used properly, OpenMP enhanced code can still be compiled by a non-OpenMP aware compiler. Because the original single-threaded semantics are retained, code would revert to serial execution. This makes it easy to add threading with minimal code changes in order to gauge the effect on performance. Best still, threading code written with OpenMP is compatible across a range of operating system platforms. A developer can choose to use pragmas or API-based integration of OpenMP based on preferences or application needs. Once the decision to parallelize a given section of code is made, it may be useful to fine-tune the threading using the OpenMP API to achieve even better performance. This choice of how to enable threading provides more options, enabling you to attain the best possible results. Sequential applications execute all instructions in a predictable manner. This provides safety by eliminating the need to lock data and prevent data corruption. Parallelizing an application without OpenMP can make it easier to introduce data corruption and overall application instability. Knowing when to lock data and how granular that locking must be can make the difference between high performance and lockups. Writing safe code with appropriate locking using low-level threading APIs is a challenge and frequently leads to tricky debugging sessions. Integrating OpenMP means that Daniel can primarily concentrate on application logic, as though instructions will all run sequentially. At compile time, the necessary additional code will be inserted to create new threads and assign work as necessary. This simplifies the flow of code and greatly simplifies debugging. Understanding some basic terms is essential to learning about OpenMP. Much more information can be found in the OpenMP specification and other materials that are on openmp.org. A directive is a pragma incorporating the literal OMP, followed by specific keywords and a new line. These are the commands that instruct an OpenMP-aware compiler or precompiler to generate the parallel-enabled code from the serial code. A structured block is any statement, single or compound, with only one entry and exit point. No jumps into or out of the statement is allowed other than a call to exit. You should be able to enclose a section in braces for it to be considered a structured block. A construct is a statement consisting of a directive and a structured block. Not all directives form a construct. A thread is an execution entity with a serial flow, its own private variables, and access to shared variables. Threads are created in response to OpenMP directives as teams. A team is composed of one or more threads created together and dedicated to the execution of a given construct. The master thread is the initial thread of execution from which teams are constructed. A parallel region is a construct that will be executed by a team of multiple threads. This can be contrasted with a serial region. A private variable is a block of storage visible and accessible only to a given thread. This can be done by declaring it within a parallel region or by using various directives. A shared variable is accessible to all threads in a team. In this example, the program will find all prime numbers between two integers by dividing the number in question by all numbers from 2 to the square root of the number. As soon as a factor is found, the search will stop. If no factor is found, the number is declared as prime. The OpenMP pragmas divide the work of the loop between multiple threads. Because testing large numbers necessitates more factors to be tried, it can easily lead to a load imbalance across the threads. Assigning iterations of threads properly can make a huge difference. Notice that the threaded block of code need not occur in a separate method. The first directive makes it clear which variables should be maintained privately per thread. By default, data is shared. The second directive converts the for loop into a parallel workload for faster processing. No explicit locking or data sharing need to be added, and simply removing the directives would allow the code to run as sequential code once again. Implementing OpenMP in an application necessitates an OpenMP-enabled compiler. Daniel is already well prepared for this, as the Intel compilers interpret OpenMP directives, while the Intel threading tools, Thread Checker, and Thread Profile support analyzing and debugging OpenMP-enabled applications. Because of the built-in support for OpenMP, no preprocessor is required to interpret the directives. This simplifies the process and leads to tighter code taking advantage of all of the Intel compiler capabilities. Through the use of Intel compilers and threading tools, Daniel gains the ability to prototype, develop, and test multi-threaded applications without switching to other toolsets. Multiprocessing, once the exclusive domain of server rooms, is more available than ever with multi-core and hyper-threading technology processors even on home desktops. End users will demand more speed without losing any stability. Throughout the development lifecycle, OpenMP enables advanced threading. Its ease of use simplifies testing various threading strategies with minimal changes to code. As the project progresses, a developer can add additional directives, fine-tune the ones already present, or use lower-level APIs as needed. Overall development time will decrease, as you will be able to locate problems faster and earlier in the process. Being able to recompile as a sequential application makes it trivial to see if errors lie within the code itself, or if they are artifacts of parallelization. The Intel C++ compiler is a drop-in replacement for the Visual Studio compiler and helps realize enormous performance gains with no additional effort. Advanced compiler switches can bring about even further benefit. Intel offers additional tools to further optimize code, especially for multi-threaded applications. Using Intel threading tools, Daniel can determine the critical path of an application, detecting deadlocks, race conditions, and data corruption. For advanced threading with minimal integration effort, look to OpenMP with its library of directives to parallelize code while retaining the single-threaded semantics throughout. Use Intel vTune along with the Intel threading tools to gain a clear picture of your application's performance. Take advantage of multiple cores and multiple processors by parallelizing wherever possible, whether through explicit threading constructs or libraries such as OpenMP. See how the Intel C++ compiler can help you achieve better results with no changes to your code. Prepare for multiple cores and processors to become even more commonplace. Optimize your code for parallel execution today and stay on the edge of the curve. For more information about the Intel compilers and threading tools, you can visit the homepage on the web.